I believe I'm sharing the screen now. I believe you can see my screen now.
Yes, sir. Yes, sir.
What can you see? What can you see?
Probing the invincible.
Okay, good. All right. So now probing the invisible, meaning that what is something that's invisible, that's something you cannot see now, right? So now we want to now probe something you cannot see. So meaning that you want to go into the earth interior, you want to do more investigation to see what do you have in it. So this helps to describe earth interior, the earth interior structure and internal forces revealed by seismic method. That's just the most important method that was used to know what we have within the earth. Yes, gravity also could have done one or two things, but from understanding and from history, it is the seismic method, especially through earthquakes. Okay, let's move ahead. So the problem is actually how do we know what's inside the earth? So the challenge, the direct observation, with direct observation is impossible. Makiola for covenant, not here now. I don't understand. Are you responding to a question?
No, sir. No, sir. Not this, sir.
Okay. All right. So the challenge, I said, the direct observation is impossible beyond a few kilometers, meaning that you can do direct observation when you are just dealing with few kilometers. In fact, okay, let's just assume that. In fact, to me, I would have loved to say, let me put few meters to kilometers. Because to, you need few meters to kilometers. We require indirect geophysical probes. The direct observation is when you drill. Basically, when you drill, so you can drill few meters, maybe up to a kilometer. I don't know. I think so. Yeah, because when you drill for hydrocarbon, you could go up to a kilometer. Yeah. All right. I think that settles that. So meters to kilometers. Now, how do you now go beyond that? How do you get information beyond that? So we have to do the indirect geophysical probes, and which is what we call the seismology investigation. This probing using seismic methods. So earthquake and large explosions generate vibrational energy waves. Explosions from dynamite, from bombs, and also what we have when there's earthquake, this generates vibrational waves that travel through the planets, meaning that they travel very, very long distances. By analyzing these waves, we can image the interior, which is analogous to a CT scan using sound waves. So in CT scan, we use seismic waves. We use sound waves, sorry, not seismic wave now. We use sound wave generally. And even but uh, uh, in seismology, sound wave in seismology. All right. So um, just give me 1 minute. I want to check something. Okay. Um. So, like I said, so okay. Um. Earthquake are large explosions generate vibrational energy waves that travel through the planets. By analyzing this wave, we can image the interior, analogous to a CT scan using sound wave. So, sound waves are sometimes seismic waves because when you detonate too, there's a lot of sound to it. But mostly, not all um, seismic wave produce sound. Yes, I think that is it. Not all seismic wave produce sound because, like shear wave and all that, they don't produce sound, but they are all mechanical waves. So, but that is not the discussion for today anyway. So, what else? Okay, the 1909 Moho discontinuation. The full meaning of Moho is Morovich. Or I don't know if you can pronounce this thing very well. Moho. We call it the abbreviation of Moho. Is cognitive discovery, which separates crust from mantle. Crust from mantle was the first major evidence of layering from seismic data, meaning that this person in this year, 1909, but I don't know, my great grandfather was not born at that time. I think so. Um, so this experiment shows that there's a discontinuity based on sections. No, it's not. It's actually refraction, seismic refraction. It shows that from mantle there's a refraction of the earth wave. So this shows that the earth are in layers. That is what this summarizes. I think there's something that I don't know if I have it here. Okay, yes, I have it. That further explain that. Okay. Now, so um seismic energy wave. Okay, please you can ignore this. There's typographical, error here. So if I have time, I will correct it. I'm just seeing itself. So this is just to show another schematic of Earth and its interior. But I gave you one that is very good as well. And this tries to show the different reflection and reflection. I have other, that is clearer than this. Let me see. Epicenter and blah 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 blah. So now let's start with itself. So the essential tools, seismic wave. We have two types of seismic waves. The first one, this thing I think we discussed in year one, so I will not dwell too much on it. The body wave and the surface wave. The body wave, we have the P wave, we have the S wave. Um, while the surface wave, we have the Rayleigh wave, the Low wave, the Stoney wave, and all that. So body wave travel within the layer itself, within the earth, travels within the earth body. While surface wave is always at the surface, at the boundary, within the crust. That's why surface waves are most responsible for earthquake. So you have further information, regarding that. Okay, I gave you the schematic of what that is. So primary wave is moved this way, like this, from left to right. Direction of propagation is parallel to direction of particle motion. These are the particles. It will expand like but that is typically how earthworm how they move. So this is S wave. It moves this way. Particle motion is perpendicular to the direction of wave propagation. So, moving this way. The layered earth is seismic revolution. The seismic data reveals a planet structured by both composition and physical states. Geology, the physical state of the earth. Now, so let's discuss the composition first. That we have done before, so I wouldn't waste time again. We have the crust, we have the mantle, we also have the core. So these are the thickness of the core. Um, also that of the mantle and also the core. Now, the radical layers within the mantle and the crust, meaning the physical states. So the lithosphere is rigid, the atmosphere is ductile, partial molten, the mesosphere more rigid again due to immense pressure. So we can't. This is more. The mesosphere is located downward. So let's see if we have the combo. Okay, this is what we have. The discontinuity I spoke about. Uh, hold on. Okay. Um, the first discontinuity is called the conoid discontinuity. Is between the upper and the lower crust. The upper crust and lower crust. Then it's somewhere here. It's just like see the partition this into two. Then the next one is the Moho discontinuity between the lower crust and the upper mantle. And see, this is they have the upper crust and this is the lower crust, and this is the upper, this is the mantle now, the upper mantle. This very line is the Moho discontinuity. This is what Mohovirovic did in his experiment in 1909 to show that there's a discontinuity. That means it helps to discover what we call the mantle. The repartite discontinuity between the upper, we have the Gutenberg, we also have the layman. You can see at different boundaries, at different boundaries. So I feel I have something to show different all these atmosphere. Okay. I don't have it here. Okay. You know what? Let me see. I would like to show you um hmm, okay. If I can get it before I send this document, I'll try and see. Um okay, probably it might be difficult. I'm thinking of having a schematic of the earth crust that will show different parts. Okay, I think the first slide, that's when I I included it in the first slide, where we have the different lithosphere. We have the upper crust, lower crust, mesosphere, and all that. So, but because this is within the mantle or crust, all these lithosphere, asthenosphere, they're just within, they are embedded within the mantle stroke crust. That means the upper mantle stroke crust. That's where we have all these stages or these layers. Okay, so because from my understanding, it is not continuous. You can see, you can easily locate it in a place, you won't locate it in another place. All right, so that's why most times you don't see it in diagrams. They will just lump everything as either with crust or with mantle. So, but within that, we have the lithosphere, the asthenosphere, the mesosphere as well. Okay, let's go ahead. Cause discovery and the shadow zone. Now, what's actually made this discovery to become popular or to be accepted is because S wave disappeared beyond 103 degrees from the epicenter. P wave are also absent between 103 and 143, the P wave shadow zone. I will explain this in the next to buttress this inference. It means that this provides irrefutable evidence for a fluid layer that blocks S wave and refracts P wave sharply, meaning that the with this energy, maybe through X wave, because I don't think dynamite will be strong enough to transmit energy to the Earth core or to the Earth mantle. So basically through Earth movement itself, earthquake itself. You notice that the signal that was sent, the P wave that was sent, at beyond a particular degree, it was not found. That means it was refracted. It was refracted. Whereas S wave disappear, that means S wave did not pass through it at all. And don't forget, S wave does not transmit, does not move or does not propagate in liquid. So because S wave did not move through liquid, that shows that there are some part of the Earth core or there's a part of the mantle that are fluid in nature. That is what gives rise to that theory that some of the Earth's subsurface are fluid in nature. If I don't know, okay. If you go back to the first week one slide, you will see that you have outer outer core, inner core. Outer core is liquid. You will notice that. So this is what that explains. So shadow. So because of that, there's no propagation within that area because of refraction. Because the P wave was refracted. So that place is called the shadow zone. The S wave shadow zone, the liquid outer core cannot transmit shear waves. That's why we have the S wave shadow zone because it did not transmit. Then why the P wave, the dramatic refraction of wave at the CMB creates a zone where no direct P wave are detected. Sorry. Let me check something. So the inner core later studied, later studies by this person identified reflections within the shadow zone, leading to the discovery of the solid inner core. Example, if a major quake occurs, Seismic station in Europe will detect P waves, but stations in Central Asia, we're doing this diagram, away will not receive direct P waves. So you can see if this is the epicenter, you can see shear wave pattern. You can see because the mantle is solid. So both P wave and S wave will move. But the core, the outer core liquid, you see it. You can see only S wave you can see. So that means this is the shadow zone. There's no imaging of all this place. But look at the P wave. Because this is liquid, but P wave propagates within liquid, there's a refraction. And also it now transmitted later. The same thing applies. But this is just a schematic diagram anyway, to just show that because of different layers, there's change in direction of propagation. So, but even at that, there are some small area, small, zones that are still regarded as shadow zone. But for P wave, the shadow zone is very small. The area for shadow zone or the arc for shadow zone is very small compared to what we have for the S wave. Seismicity and plate tectonics, the map of internal process. So earthquakes are not random. It delineates plate boundaries. So these are different types of plate boundary. Yeah, one we have done this, so I won't speak too much about that. Now, this means that seismicity is the surface expression of the Earth's internal heat. Surface expression of the Earth's internal heat engine driving plate motion. The pattern of quakes reveals the geometry and dynamics of plate interactions. If you still remember, well, I think I'm not sure because you guys are we are working on CCMAS now. So, but I know I think it's a year three course for geology or I think both geology called plate tectonics is a course on its own. So I don't know what it will be for you. If you are still going to do a course called plate tectonics, I'm not sure, but I'm very sure that there was a course like that. Or there is a course because we are still hosting it anyway. That the year three students take plate tectonics. All right, so um, a map showing different plate boundary. Plate boundary. I wouldn't want to even talk much about this because I remember we have what we call Pacific Ring of Fire, where we have Arctic earthquake and all that. But this course is not earthquake major. So probing a major boundary. So the abrupt changes in seismic velocity defines major boundary, and that is what you have to live with. When you have change in seismic velocity path, it shows that you have moved from one boundary to the other because the properties, the boundary has different unique properties. If we have two layers, they have the same properties. There won't be any change. So it will just go. The, the boundary will not exist, even if the layers are not the same. But if the properties are the same, there won't be any boundary. So the core mantle boundary is marked by a sharp drop in P wave velocity from let's say 13.7 kilometers per second to 8. If a P wave traveling at an average of 13 kilometers per second through the mantle takes 10 minutes to reach the core mantle boundary, what is the appropriate depth to the boundary. Since I've given you the calculation, so I won't start, I won't talk about that again. So you can see the solution for your okay. I think that is just I think that is what I have for you again regarding this. And so we have a scenarios example one, the solution, example two, the solution, example three, and the solutions as well. So these are things you should do. You should go through them. Okay. Any question or clarification? Okay. Okay. So next week, when is convocation? I think it's upper week. Convocation is upper week, I guess.